Yeah, hey. So I'm going to try and convince you that structural imaging can be done better, and that's actually quite easy to do so. Um, so, oh. So arguably, since people have been scanning people, since neuroscientists have started scanning people for the experiments, there's been a lot of innovation and progress, as is very evident by days like these on methods days, etc. An obvious example is moving away from what is now often called blobology into more pattern-like analyses like Nico's RSA, for example. So functional imaging has seen loads of innovation. White matter imaging has seen innovation as well. So for example, we're now able to track white matter connectivity like this using DTI and other things. However, when it comes to gray matter, there has been a little bit less change and innovation in the last, say, 10 to 20 years. In fact, people tend to use methods that were developed largely in 2000, 2001. One of them, as I'm sure all of you know, is VBM, and as you can see here, it's still being used widely, even sort of this year. The slightly different approach, or rather different approach, is surface-based analyses, also being used a lot. In general, the surface-based analyses, when you do that, you tend to calculate either volume and or cortical thickness. And that's good, that's interesting information. So we use this sort of shape-based way of tracking volume and thickness. However, if you look at the brain like this, at the real human brain, you might argue that something like volume and thickness is a bit of a coarse measure of what's going on structurally and biologically in the brain. So the brain actually curves in different ways, it folds in different ways, it has different levels of depth at different points, but thickness and curvature and volume don't really get at that quite properly. So we might want to ask whether it's possible to calculate better and more interesting shape measures in addition to volume and cortical thickness. And so this is where Mindboggle comes in. Now Mindboggle is, maybe can I see if anybody has heard of Mindboggle before? Yeah, cool. So a few of you. Basically, it's an open source brain morphometry platform. So this is just the website. This is the main paper that came out last year in 2017. It was developed by Arno Klein and quite a few other people. The list is always growing. It's free surfer-based, and the main mission is to improve the accuracy and consistency of structural imaging. So the input are T1-weighted MR images, and the output are a whole range of shape measures. Common ones like volume and thickness, and more novel ones. Now I want to say at this point, it's not so much that Arno Klein and etc. have invented all of these new ideas, but rather that actually there have been quite a few labs in the past few years who have been trying to create novel methods, but they've been going about it in rather different ways. So there hasn't been very much consistency about this. So the idea of Mindboggle is to have these relatively novel methods or measures, but to have them with more accuracy and more consistency, and to be able to calculate those quite easily. And I'll show you how easily at the end. So what am I going to do now? I'm going to tell you about a couple of those novel shape measures, and also hopefully show you some data, the preliminary data of my analyses, in which I looked at how these metrics correlate with age, and hopefully convince you that there are improvements to be seen there. And I'm also going to show you how you can implement Mindboggle if you wish to do so. So I said Mindboggle offers you a whole range of measures or metrics. In addition to volume and cortical thickness, you also get Thickinthehead, that's what they call it, depth and curvature. And interestingly enough, you get all of that for brain regions, but also for sulci. I should say that there are a few other metrics that Mindboggle outputs, but I don't really have time to cover those today. But those are, I suppose, the main ones that one should know about. So I'll explain those now. So Thickinthehead is arguably a better thickness measure. So here is one of the problems about thickness measures in, for example, FreeSurfer. So what you can see here in dark gray is the cortical thickness. That's just the gap between, or the difference between the red line and the green line. And if you register, or if you reconstruct your structure images well, then you get pretty decent, really good actually estimates of cortical thickness. However, FreeSurfer and other software actually has some problems with reconstruction, and that's largely because when they reconstruct, they use only one type of size of voxel. So you reconstruct your image with, say, 1 millimeter voxels, and therefore what happens is that you'll miss some bits sometimes. So for example here, you see that there's actually a fundus, but you can't really spot it, it's not been registered. Similarly here, there is a sulcus, but it's not registered again. So the solution to that is to offer different size voxels, smaller and larger ones, depending on what you need there, in your reconstruction. So that's basically what Thickinthehead, and again, I have not covered this word, they have, avoids. So it avoids this reconstruction problem by offering various voxel dimensions, so for example, from 0.5, say, up to 1. And this will give you a better representation of the cortex contours. And so this is just an image of the FreeSurfer, of the Mindboggle paper. The idea is that you've better traced this, so therefore you get purer, better thickness measures than you would otherwise get them. The different colors simply indicate the different regions of the brain. That's Thickinthehead. The next one is Curvature. So the idea is that curvature is a measure used to quantify the complexity of cortical folding, and it's based on the relative direction of normal vectors in a small neighborhood. Essentially what that means is that you get maps like this, and so you have sort of like a difference of scale of curvature that indicates how curved any one region of the brain is. And the way to quantify curvature is by either having it curving outwards, convex, or curving like here, for example, right there, or curving inwards, concave, like right there. The way that, so I was very interested in curvature. This is kind of like how this project started for me, because I thought that it might tell us something really cool about aging. Because basically one of the things that we know about aging is that as people age, their brains shrink, so volume reduction. And I thought, well, if the brains shrink a bit like a balloon, then we should find increased curvature on the outside. So if you take the air out the balloon, you should be able to trace more curvature outside on the surface. And I'll come back to this idea in a bit. So the third one that I wanted to talk to you about is depth. Essentially, it's arguable that it's actually really important to characterize the highly folded surface of the cortex. Also because you want to extract that surface which is buried deep inside the folds of the brain. For example, your sulci pits, and your fundi. So pits are the very bottom of the sulcus. There are different kinds of depth. One is slightly older, the other one is even newer. One of the ones that's been used before is called geodesic depth, and essentially that's this green thing here. So basically, it traces this. Sorry, let me orient you. This is a central sulcus. It's taken out here, and geodesic depth traces the surface, and then gives you a depth measure after having traced it like this. So from one point to the other. The problem with that kind of depth measure is that it is sensitive to irregularities in the surface. So if you imagine, for example, here, that there is sort of like an artery or like a vein or a cavity in there, then this green thing would like go around it and then trace back up. So it would incorporate things that aren't actually the surface, the depth of that say sulcus, but it would calculate it as if it were. So something that has lots of irregularities, even though that doesn't make it deeper, would be seen as deeper by geodesic depth. So to avoid that problem, Mindboggle created something else called travel depth. Not going to get into all that much detail. The main idea is that it assigns a depth value to every vertex in a mesh, and that the path estimates that you get are less sensitive to these irregularities. And therefore, this travel depth measure remains faithful to the topology of the surface. So this is just an image depicting that difference. You've got your geodesic depth up here, travel depth down here. Essentially, this is the insula, and yellow means more deeper, blue means less deep. Geodesic depth says that the insula is at its deepest on the outside of the insula, and travel depth tells you it's at its deepest on the folds of the insula, on the forget what they're called, but so the outside bits of the insula. And that's true. That is where it is at its deepest. So it seems that travel depth is better captures the sort of like biological ground truth of depth of the brain. So this is just another depth measure. So I'm now going to share with you some very preliminary data on a project that we were just doing, in which I tried to see how these measures relate to age. So the question was, is there a better way to measure neural aging than what we normally do with VBM or cortical thickness/volume? What we did is we ran this Mindboggle stuff on roughly 700 people on the CamCan dataset. When I say we, that was Tim using the HPC, the Large Computing Cluster. We pre-registered our analyses. And as I said, I'm now going to show you some results. So what I'm going to show you now is plots that correlate age with different metrics. At the top will be the older ones, and the bottom will be the newer ones. So let's start with SPM's VBM. So what you can see here is age and total gray matter. You can see that it declines with age, which we expect, with a correlation of around -2.1. Next, I'm going to show you volume. This is free surface-based volume. We can see again a decline, but at a steeper rate. Again, thickness, so decline at a relatively similar rate to volume, suggesting here, for example, that surface-based analyses have a steeper correlation with age than VBM. Now, curvature. That was this balloon idea that I had. So here, we can see that as people get older, with increasing age, we find increased curvature. So as volume decreases, the balloon gets more crumbled, there's more curvature. And we can detect that at a correlation of 0.77. Thickinthehead. This was the sort of thickness measure that's supposed to be better than what we had before. And looking at this graph, you see a correlation of -0.84, which I have to say I have not seen in the literature anywhere before, this bit that we can predict or correlate with age at such a rate or at such a value. So here -0.84. And then I also talked to you about depth. Here is depth of brain regions and age again, not so highly correlated, but also that is not such a big surprise, because if you think about brain regions, well, they're not that deep in the same sense as maybe a sulcus might be. And indeed, when you look at the depth of the sulci, we find again a stronger correlation than we found for brain regions. So looking at these simple correlations between different shape-based metrics and age, this suggests that there is certainly some interesting stuff out there. It suggests that other metrics might better capture how the brain changes with age. And that is not surprising because, as I said in the beginning, this idea that the volume and thickness are a bit coarse and a bit sort of like rough around the edges might really well be true. And this might capture some sort of like biological phenomenon that we've yet to uncover and we have been overlooking, I think, for a long time. So if this convinces you that maybe you should move on and use these other kinds of metrics if you want to look at how the brain changes, say, with age or is in terms of its structure, you might wish to implement Mindboggle. And this is where really cool news come in. The fact is that it's really, really simple to use, especially with few participants. So what you need to do is you need to install Docker like that. That allows you to sort of access all the sort of software, I guess, that you're going to need to be using. It takes a bit of time to download. You then set your environment. So this is my having done it on my local computer here at the CBU. And basically what you do is you specify your image, your T1 image. Here, for example, I'm specifying the T1 image for this participant, 1 to 1, and so forth, giving him some ID or them some ID. And you're sort of like docking on to the host, so anyway, so you're defining your environment like this, and that's all you need to really do, so these 4 lines, and then once you've defined it, you run one line of command, and this is it. And this line of command takes a few hours, around 7, 8 per participant, on my computer anyway, and it'll give you all of these output metrics that I have talked to you about, and some more, which I didn't have time to cover today. So all of this is available online, all of these guidelines, I guess, or rules, and it's pretty easy to follow. The idea, again, is that now we have a way to get interesting, novel shape measures in a way that's more consistent and more accurate than what's been around before, and it seems that they have something interesting to tell us about the brain. If you have more data, things do become a bit more difficult. So if we had run our 700 or so CAMP-CAN participants on my computer, it would have taken us 10.5 years. So instead, we ran it on the HPC, where we managed to do 100,000 computing hours in around 10 days, 10 to 14 days. Tim Keatsman wrote lots of batch scripts to make that happen. So if you are interested in running Mindboggle on a large existing data set, I suppose that's possible. Not quite as easy as here at all. It will take some more work, but you're very welcome to speak to Tim about this if you're interested in that. And with that, I'm finished. I just want to thank the people who've been working with me on this project, which is Tim, Anthony, Delia, Roger, and Rick. And thank you very much.